Section 9.11. Activities are defined with respect to standard states. So if you have a, let's say, ideal dilute solution, for the solvent, you use a standard state. For the solute, you use a different standard state. Let's look at this. For a solvent, in actually not only in ideal dilute solution, in most solutions, as long as the mole fraction of the solvent is greater than 0.5, the solvent is the majority, and then we use this pi star as the standard state. So the activity of this solvent is equal to the vapor pressure of the solvent divided by the vapor pressure of that pure solvent. So when x approaches 1, you have a pure solvent. This A approaches x. Alright, so these two are close to each other. When the solution contains mostly the solvent, because it behaves really like the solvent. Again, if you have a 0.1% sucrose in water, 99.9% of the substance is water. Each water is surrounded by other water molecules, so it's convenient to use pure water as the standard state. But for the low concentration solute, we use a different standard state. Now I'm going to give you a different example. Let's dissolve oxygen in water. Let's maintain a 1 bar pure oxygen gas on top of pure water, and then this water may dissolve a little bit oxygen. Let's say 0.01% is oxygen. The mole fraction of oxygen is 0.0001. Okay, so that's very low. In that case, in a solution, each oxygen molecule is now surrounded by not by other oxygen molecules, but by water molecules. So the chemical environment for the solute is completely different from the pure solute. The chemical environment changes. The attraction between oxygen and water is so different from the attraction between oxygen and the oxygen. We have to use a different standard state. So this time, what standard state do we use? We are using a extremely diluted solution of oxygen as the standard state. For convenience. So in that case, when the mole fraction of this oxygen approaches 0, its activity approaches its mole fraction. So again, for oxygen water, its activity is defined to be the vapor pressure of oxygen divided by a different standard state. It's Henry's constant. This Henry's constant depends on both the solute and the solvent, because the attraction between the solute and the solvent and its difference from the pure solute, the difference between the attraction between solute and solvent and the attraction between solute and solute makes a contribution here. Therefore, this case of H is used instead. That's a hypothetical state. So we actually measure the this A. Actually, we measure this X in the low concentration region. When the concentration is low, we assume this A is approximately the same as X, so we plug in X here. And also, we can easily measure the vapor pressure, and then we determine the Henry constant. For example, if the vapor pressure of a substance is 1 bar, its mole fraction is 0.0002, very low concentration, and then we plug in this mole fraction in here. We plug in the pressure in here, and then we calculate the Henry's constant. In this case, it's 5,000 bars. So, hypothetically, if you apply 500 bars of oxygen on top of pure water, the mole fraction is going to be 0.1 for oxygen. But again, this is a hypothetical state. This is useful to make predictions for low concentration regions. So the example I give you that contains 500 bars of oxygen and 0.1 mole fraction of oxygen in water, That's just a really rough estimate. I think it's very inaccurate. But if you are talking about just 1 bar or 0.1 bar, I think this Henry's constant is very useful for predicting the very low concentration of the oxygen or nitrogen or whatever low solubility substance in water.